very weird because, as we expected, if we forecast the next hour, we, we should we should obtain something better than predict the next 3 hours. So the problem it was the opposite because in 3 hours we have something much better than 1 hour. So it was a huge problem because we discussed a lot, and finally we analyzed the the distribution of the velocity from the database, and we obtain this. It's practically all the velocities of the scene. It's around 0, and the distribution is around 0.27, 0.17, 0.13. So it's pretty much similar to the other. So my conclusion is this data it doesn't work for neural network because neural network needs a huge distribution of the different velocities. So in this case, the model it doesn't work in any case because for the it's practically for how it's distributed the data. So and for example, the best idea is we don't need a Gaussian distribution in a better thing. It's much better a uniform distribution because the neural network will see different values. So the idea is generalize everything. So the slope was practically this curve. And okay. So the conclusion of this work is this work improved the estimation of the scene using neural network with the previous work with the dark. The autoregressive model it's much better because we obtain the error around 0.1312 and the error is like 0.08. And for the operational context, this is not mentioned in this work, but the problem with random forest, the weight of the model it's around 8 gigabytes, so it's huge. And we need a lot of memory RAM for the server. Instead, the neural network is around 200 megabytes. So it's really nice for small servers, and also it's pretty much it's faster because the model that I found in random forest was in sklearn, and this one worked in PyTorch, so it's much better in that case. And also, the other problem was the database using for the forecasting is not the optimal for the model because the sensor, okay, everything is in the web store of Paranal. So the problem is we don't have access to the sensors, and these sensors only get the information of the scene every 80 seconds. And as you know, the turbulence it's much faster. So for get information of the scene and post-processing is very nice, but if we want to include the system, we need more sampling because night quiz or and everything. So we're still working on this, but at the first view is the neural network need to subtract the information of the time series. So the current neural network doesn't do that because the sampling. Instead, the random forest is too random that in this case was better. So that's the conclusion of this. And the other problem is the neural network needs more data from the past to predict the next hour. So it doesn't work from 1 hour to 1 hour. We need to extract more information like, I don't know, for example, TimesNet, take the Fourier transform to get the frequencies or something like that. But in 1 hour, we don't have enough information for that. And okay, for the next, for the other astroclimatic parameter, please read the paper that we are working with. And that's all. Thank you very much. Any questions?
Previous slide. I want to put having the regression model compare the random forest and the other models like long short-term memory models, do you, like, in the first one on the left one, do you concatenate time series, and in the other one you use them as channels? I don't know if I understand the difference.
Okay, here we have random forest only work in one channel. So you have to put all the information. For example, you can put the scene in the, I don't know, the first 20 values and the pressure in the next 20 values, or you can mix it like here. Because the random forest, it's so random, I really don't like it. And it's working this way. It selects one value and compare it randomly with other value. So this one doesn't it doesn't care about the sequence basically. But in this case, the long-term model analyze separately every signal for every channel. So that's why it's much better work.
And what is a channel is like timestamp. So time at t equals 0, you have certain data, and then
Yeah, let me. Okay, probably this is the other flow. No. Okay, so we have here different parameters. So every parameter is a channel. Okay, so for images, for adaptive optics, you can work with different channels. One is blue, red, or and green, and you can work as you want. So you can put, for example, the I don't know the pyramid. You can put every slope, but no, every subpupil in different channels to analyze separately. So in this work, we separate the batch, the sampling, the time series is going here, the batch is going down, and the channel is everything. So that's why it's more easy to work with the LSTM because you can work with different values of the signals. So it's for example, it's depending on the neural network at the end. But for example, the convolutional model, the convolution in time. So every channel analyzes the convolution of the sequence, and at the end it's concatenated in a black box. But it doesn't work if we put everything like this because the convolution is very bad if you mix the values.
how does it even understand time information that is not captured in the network?
Sorry?
The time sequence information that is not computed. It's not.
I don't know. I never try if I mix everything. So I just put everything here because it was more easy.
Yeah.
My database was generated like this one, so I put I just include some flattened. It was a reshape in the number of batch and the number of segments multiplied by the feature.
Any other question?
Okay. The saturation of the neural network is okay. We, for example, in the first using 1 year, actually this one, 6 with the beginning of 2017, the error here is more higher than this one. But if you see here, for example, the LSTM sequence to sequence, okay, here going down and here is stuck, increase. So the standard deviation of the error from here to here is practically negligible. But here the step is very high compared to the next years. So okay, the recommendation is use all the years that you want because the neural network will be better because you have more distribution and example, but you need as minimum 2 years to obtain something that you want. So that's the point of this.
You also showed that you use TCNs. Don't you need image data for TCN models?
Image data, it's depending how you modify because this one was implemented for temporal space.
Yeah.
So it's So practically every single neural network you can use it as you want, but the performance will be different. And I found this one implemented for temporal series and forecasting. And also, for example, here, this is only it's not the state of the art, because the state of the art is the best one was the transformer neural network, but I didn't put the information here because I'm still getting some information about that. I'm still trying and measuring.
Can you also comment on, like, if you compare transformer network TCN and STM, if there are also some requirements, okay, maybe for transformer you need more data as compared to?
Yeah, probably yes,
Okay.
but it's take more to train it,
Yeah.
because I'm training with my laptop for now.
Yeah.
We are getting in, we are collecting money to buy the server, but actually it's depending on each neural network to get the improvement, because every single neural network depends of how deep is your neural network, the number of layers, the hidden size, and also, for example, the TCN. They say that it's more easy to train it because it doesn't require a lot of data.
Any other question?
I was wondering if you had like a series of like the seeing and the temperature, like all of that input. I was wondering if you looked at if you didn't have all of that input data, like you only had some of those parameters, how that affected the content.
Hi, it's a good question. Okay, this this paper, they analyzed. It was analysis only with random forest. So in the LSTM and the current neural networks, we have to do it again. But here they found that there are some parameters that are much better than others. So I'm using the database, using the parameters obtained from here. And also I would like to review everything, because the neural network works in this different way of the random forest. But only for time, we say, okay, my boss told me, we want to compare your result with this one, so you have to work with the same parameter. But for the next work, I will analyze this with different technique, like I think it's called incidence score or something like that, that analyze how the different parameters modify the forecasting of the market.
So this is maybe a broader question. I don't know if it's answerable, but what if you use also sort of the weather forecasting models from around the site to your advantage? You know, the wind speeds are higher a few kilometers away and they move in your direction. Can you use that in your prediction?
Okay, it's a good question. The problem is I don't have the information from Panama. They have everything on site from the historical views. But okay, we have to discuss that, because we have information of different altitude of the velocity. So for now we are working with the velocity at 30 meters of high. So it's practically in the level of the telescope. So yeah, probably the forecast will be modified with that, because you will have information from the future at the end. Because if you know, if you are, I don't know, 20 meters of the other measurement, and it's moving in, I don't know, 5 meters per second, so in 5 seconds you will have that mass moving over you. But yeah, we have to analyze and discuss that. But the problem is the neural network, they doesn't know anything about the data, so they practically mixing and analyzing everything. So the idea of this on the next work is use the neural network to improve the estimation of the AR model, instead trying to fight one each other. So my idea is not use the neural network to replace something. The idea is improving everything. So if we have something very nice and we found some problem in that model, we can use the neural network to fix that problem and improve everything. But probably if we get the information of the wind speed to some points around to the telescope, should be much better.
Any other questions? Last question, so we can move to the schedule.
Yes. So when you train the model, you have many data like pressure, temperature, seeing. What's the output? Only the seeing, or do you also predict all those like temperature, humidity?
Okay, good question. The output is on one channel and it's the seeing. So for the pressure, you have to train another neural network, because if you work with different channels in the output, your loss validation will depend on the scale of your value. For example, if you work with the CN square, the dimension of that is so different with the scene. And for example, the pressure here it's in hectopascal, so it's like 745, and the scene it's around to 1.5. So if you put your loss for your training, you will have a mess of data, so the error will increase. So my suggestion is to work everything separately or normalize your output, because in the same range you can train everything, but also you will increase the number of output. So in this case we have it was 30 points time series, and if you and we put 12 parameters. I think it's too much parameters. So at the end you have 30 multiplied by 12. So the error will be huge, and the neural network will not improve any estimation separately.
Okay, thanks Camilo again. So for the next presentation, here is Professor Tambera from Optola.
Hello. Thank you guys for sticking around, and hopefully you don't fall asleep like my students often do. And so basically, we just summarize a little bit of what we've been doing, and so some of these was in my talk, of course, recycling a bit. But overall, well, it all started with this. I mean, this maybe at the time many people believe it was kind of a silly idea, but we believe it was a cool stuff, but we didn't care. So basically, that's the whole idea here was that we thought that a waveform sensor was anything that we can get an intensity measurement, and we can force it to learn a wavefront or a phase that explains that measurement. Basically, that's the whole idea. So the key point of this is that we were able basically to open this design space here. That basically we can, from an imaging sensor that's getting the PSF, or either if you're doing pupil plane or whatever kind of something in your optics, and at the end of the day you end up with a measurement, an intensity measurement, and we want to map these intensity measurements as one-to-one as possible to a unique phase, because that's the a classical problem of phase retrieval. So phase retrieval is kind of ambiguous. You can get sometimes some positive and negative, let's say, focus or defocus, and that's why sometimes you need more than one measurement if you want to retrieve phase out from intensity measurements. And the good thing here is that we realize that there's some better transformations to allow and remove, all these ambiguities of the inverse problem. Okay, so that's the whole trick behind it. And so we came with this idea of a very generalized idea. So basically the phase comes and passes through this optical system. We have a sensor, basically a 2D intensity detector array. From this measurement we have to go through a phase reconstruction. But basically we'll hopefully have a system that delivers you, hopefully directly the phase, which is kind of the difficult part in optical systems, at least in the visible or invisible stuff. So anyway, And the first approach, of course, we took was the most naive one. Was basically, okay, let's we know some systems, they work, so let's not mess with them, and just let's try to mess and improve the reconstruction, because we know some of them have issues with the reconstruction, and knowing something as well that you will find out. So all this neural net stuff, I mean, sometimes they are tricky to train. They will take some long time, especially today that you're going to train a very hardcore one. But the thing is, after you train, this whole inference process in the network can be very fast. So it can become very competitive, to some of the traditional methods that need to do, some matrix inversions and other things involved, during the reconstruction process. So as the dimensionality scales, I mean, that you need, more phase resolution and more modes or whatever. So that process can be very streamlined for real-time stuff. So that's a very good news. So anyway, so in that regard, of course, we start with our huge friend here, the pyramid, which we were convinced, okay, this is the one, and this is the one you have to work with, and that's where Camilo suffered a lot, trying to make it work. Basically train this stuff. I'm trying to find, okay, a good neural network to match the kind of intensities that were, produced by the pyramid. And of course, you can look into that, and you will see that the network works very fine. I mean, we were really surprised to see how robust it was. It was trained under, of course, he put all sorts of open loop and closed loop strategies to make it more robust. So it started learning different, distribution also of the data. He put some noise, and it was really, really robust. And at least in our experimental stuff, that is basically what we have in the lab, which is full post, were very fine. But the good thing is that we were able to move on. Basically what we did at the beginning of the year is that when we went to OHP and went to Papyrus, we basically put the same neural network on the system, and we put it on the sky, and it worked. So that was very cool demonstration of it, of how robust it was. We didn't care about spiders, obscurations, anything. And it worked. So it's a very, very cool stuff. Anyway, so of course we are not only happy with that. Something else we've been playing around for the last years, and this is something we've been working with a lot with Felipe. And it was the idea of, why messing around with the reconstruction? Why not messing around with the optical system itself? Well, how can we make the optical system to do better measurements? That more close to what we want. And that's what we've been doing. I mean, especially Nico and Felipe, they came with this idea, okay, let's put something else, an extra layer of optics besides the pyramid. So this was all built on top of the pyramid. So basically we let evolve different versions. In this case were some diffractive layers, training with the same machine learning approach, the same data. So at the end of the day, they were able to linearize the response of the optical system. So the behavior we got was like we were actually acting as an optical modulator, which as a passive modulator at the end of the day. So it's doing some distribution of photons in some ways very similar to the modulation, but without any mechanical parts. So that's a very cool stuff as well. Of course, we had some a trade-off with sensitivity as well. I mean, the pyramid is an awesome device by itself. So if you modify it, you will always have to take some bit from it. But anyway, it was very, very cool stuff. And but we didn't stop there. We say, okay, we should move one step further. And the step further, we say, let's do the whole genetic approach. So why not allow not only the optical system to evolve, but also if we know this neural network is so good, so why not keep using them? So basically what we are doing now is that we allow the optical system to try to adapt the measurements that better suit the way the neural network works. So basically we are obtaining an optical system or a wavefront sensor that basically try to match as best as possible what the reconstructor is expecting. So basically we can do the same with different reconstructors. Most likely we will end up with different optical systems. In the case before we were using a linear reconstructor, so So we get kind of a linear optical system. And here, we don't care if we could use a nonlinear reconstructor. Basically, we still want a nonlinear optical system, but maybe it can be slightly modified to better adapt and get the best out of your reconstructor. So that's what we've been doing with this very generic way. So basically, we network. This is the former work we had with Camilo, and this is the one that we are jointly training. So we have the optics on top of the neural network. So you see that there's a huge, a very good improvement. You see it can be faster, it's more stable. So that's what we expect. And of course, if we increase the turbulence, you still get some improvement. So that's very good. So we're able to demonstrate it. We want to hopefully test it on the sky whenever we can, whenever we're ready in our own telescope. Anyway, I would like to show you, before finishing, just another thing. So Felipe is a bit sick, the bottom there. So just only to share some other stuff we are doing. So we are also working. So there's many people that complain about, all your stuff looks nice, you make it work, but we don't like it. That's fine. Okay, that's fine. Many people don't like all these nets because they don't understand what they are doing, which is okay. That's fine. Okay, if you don't like it. So there's a lot of ideas for trying to get more explainability. So what we are doing now, so we took an algorithm, which is an iterative algorithm from the group from Linz that are working hard on these nonlinear reconstructors. But the problem of these nonlinear reconstructors, they are iterative and they're fairly slow. So they can take 50, 100, iterations, that kind of thing. So, but it's very nice. Okay. But it's useless if we cannot make it real time. So Felipe basically took it and make it a new proposal. We call this neural nope. So the original algorithm was nope, neural nope, and neural nope is just a revisited version of what iterative algorithms are. So basically, there's this whole idea of what we call basically we split an iterative algorithm, and we basically turn every iteration of the algorithm into one of the layers of your network. And this is called deep unfolding. So basically people are doing this even for phase-retrieval problems. So basically treat every, the thing is that at some point you fix the amount of iterations. And then you have your neural network. Neural network is not only another thing that a fixed amount of iterations of your iterative algorithm, but now all the parameters can be trained. Because typically in iterative algorithms, you don't have that much flexibility. You have to play with your parameters, tweak them, and basically fix them or use a scheduler, just like the learning rate stuff. But here, we give freedom, any internal parameters can be, so it will know what to do with the first iteration, the second, and it will know also that we have a fixed amount. So that can be a better match also for real-time stuff. So the cool thing is that it's actually working. I don't know if there's an animation here, but Felipe, you put something? Or?
Yes, to put
Okay, good. So basically, this is a comparison of what the guys are doing. So basically, how is the open loop, and when they close the loop, it's showing good stuff. And but the good news is that so this is basically the input phase. We had what you classically can get with a matrix vector multiplication, basically just a matrix inversion, the classical linear inversion. And on the yellow thing here is what happens when you use the traditional nope, so the one proposed by Victoria, with 50 iterations, which is a lot. It took a long time. And this is the one, there's two versions of the neural stuff that are here, and they were way faster because they used, I don't know how many iterations? 10. Okay. So there's only 10 iterations, but they can still, improve, the fidelity of the reconstruction for, the behavior is very linear, so basically linearize the response. That's very cool. And so I think we are moving towards that direction, and to have explainable algorithms at least, so the mathematicians are happy, and hopefully we get as competitive results as we had before with these other transformer neural nets. So with that said, I will not get into more conclusions, but the key point here for us is that we can jointly train optics and reconstruction. That's what we also want to do with that. And you can do it with any algorithm. You can choose your reconstruction, it doesn't matter. Or you can constrain also your optics. It really doesn't matter. And so basically we can stand linearity range, we can prove we eliminate need for modulation. There's no need for modulation really. So there's plenty of flexibility. So the key point is that there's plenty of room, I mean, to design new stuff. You know, I know ISO guys don't want that, but basically for many other applications as well, there's plenty of stuff. It's not the end of the road. I mean, we're still looking for the golden pod here for the best waveform sensor ever. So we should keep working. So thank you guys.
Thank you, Esteban. Any questions? Here, sir.
In practice, optimization of the objects, how do you think to implement that?
You will see, so Rodrigo will make the next presentation. He will show our efforts in how to implement this stuff.
No digo nada.
Those simulations are fixed D over R naught?
So basically we did the same tricks we did for the never net as you guys will do today. Basically we get, because if you're aiming for linearity, basically you have to aim for a range of D over R naught where you want to work. So basically you try to understand that you're having different regimes. And that's the way you can make it really linearize the response.
And you can find an optical phase that is good for all of this range. Like
Exactly.
okay.
So basically you can design them very tailored to a specific situation, but I don't know if there's something like, something that makes it all, yet. Well, Francisco.
In the loop network, the unit is the same at each iteration, or you have different units?
It's the same one. That's what I believe. You can ask Felipe later if he can open his mouth. But
So we try both by fixing the same unit and also having a different unit per iteration, and the results are quite similar. But I think it's more easy to have one story in memory.
save your throat, Felipe, for later. Anyway, yeah.
Next one?
Which alternative will be in the case of a low amount of data? Because usually if you want to train, for instance, the transformer, you need too much data. Which is the alternative for limited amount of data?
I mean, hallucination. I mean, no, basically, no, diversity. You can have a data, you can move it around, you can shift it. I mean, the good thing is that we're doing simulation, so basically we can do unlimited data. The problem is when you want to train with your physical system, then you're kind of limited. I mean, especially in a telescope, maybe you don't have the flexibility to have all the modes or in all the conditions you want. Maybe you can do it with the DM, but and then of course you will incorporate some of your NCPA and other problems into the models. Okay, but basically, I mean, if your simulation, unless your simulation is too hardcore, I mean, really, not a real problem. I mean, it's just a matter of time, of course, in the training process, and how can you alleviate that?
Any other question? No?
I'm wondering, you did all this testing for various sensors on simulation, right? The rockets on phase and also but when it comes to on-bench testing and on-site testing, can you comment a bit? Do you think it would work having a sensor or something like a random phase distribution that you
Well, the hope is yes. So Rodrigo will show some of our preliminary stuff on the bench. So I think there is hope. It's not easy. I mean, especially the diffractive stuff is kind of a difficult monster to play with, So you have sometimes different orders, and you have to play with these orders. It's not as you don't see that all that reflected into the simulation. So going to the actual system, the behavior sometimes is slightly different, and you have to do some management. So of course we're thinking all this to work with lasers, so we don't care that much about photoflux yet. But of course, I mean, astronomers will worry about that. But then, I mean, we still have to see. I mean, we can constrain how we work with, or we can constrain the optical system basically to be, I mean, a different one, or a continuous stuff instead of being a diffracted stuff. I don't know.
Okay, another question? No, thanks. Is there any? So, Esteban already spoiled a bit. Now we have Rodrigo Muñoz. We have Rodrigo Muñoz with deep holographic wavefront sensor. Yes.
¿Cómo pasará a usted? ¿Cuál es lo del vacío?
So, hi, I'm going to present you guys some of the work that we have been doing. As Professor Esteban says, I'm being developing some holographic waveform sensors. So, for instance, I'm going to show you how to train this stuff. If you're curious about the recording, then we can talk later on the laboratory here. So first I introduced the deep holographic shock carbon waveform sensor. So we're going to talk about the dataset generation. This all the stuff is trained with experimental data that we obtain in the laboratory. So we're going to talk about the dataset generation, the training of the neural network, and then some closed loop results in the optical range. And the same for the pyramid waveform sensor, or the holographic pyramid waveform sensor. So first, we need to get the data set. So we need to flag the DM. So this whole data set is generated with the DM. So first we need to flag the DM and search the reference points of the shock harmon. And with that we can do some windows here, and we can extract not only the centroids, but also the shape of every PSF formed in the shock harmon. So with that we can then put some variations onto the formal mirror and get the measurement of the shock harmon. So how we do this operation? Well, we use OPAO, so we generate some phase screens. Then we decompose these phase screens with the certainty coefficients, and then we put these certainty coefficients onto the DM, and then we do the measurements. So we have the input to the neural network, that is the 16 channels of every PSF, and the output, the input certainty vector that we put onto the DM. That's the data acquisition that we made. I think I took like 10,000 samples with different type of aberrations. So those are the key parameters of the transformer neural network training. So we use the GCDIT XX tiny because Camilos uses it in her paper. So that's why we use I use this neural network. So the input shape is the batch size for the training, the 16 subvectors, and then every matrix of the PSF. And the output size, of course, is the 68 setting coefficients in one vector. Why 68? Because ORDM is only capable to represent all the first 68 setting vectors, setting coefficients. Then the normalization for each image or frame is C-score, because it is relatively robust to the intensity fluctuations. We train this for 200 epochs. We use the optimizer Adam and the loss MSA loss. Well, the loss I I took this loss because I have better results with that loss. Not that much to say to that. This is the whole scheme, the training scheme. So we put some input certainty coefficients onto our DM, and we generate a waveform. Then we measure with the waveform camera. We saw the PSF distorted. Then we stack this PSF, and then we do the forward to the neural network, and we have the output certainty. So then we compare the input certainty with the output certainty and measure that with the loss function, and then we backpropagate the error to the neural network. So these are some results that I have. I took it to the laboratory. So we are closing the loop with the waveform estimation, neural network waveform estimation, reconstruction. So here we have weak turbulence. We are closing the loop with that, and with the strong turbulence too, we are able to close the loop too. All this stuff is with finite numbers of certain modes, so it's not realistic now, but I think if we do some stuff with another SLM and get some relatively realistic turbulence, we can also close the with these holographic shock Harman waveform sensors. That's for the shock Harman. Now I'm going to display about the pyramid waveform sensor. So here we have two shapes of the pyramid waveform sensor. With the DM flat. So the 3 sides pyramid and the 4 sides pyramid, both holographically recorded onto a photopolymer. So this is a propagation, refractive propagation of the photopolymer. So you can see, I don't see many difference with the real pyramid. So then we get the coordinates of every pupil, so we can, let's say, choose the information of the pyramid. So with that, we can then, as the shock Harman, then we can stack every pupil, and then we can forward this to the neural network. So it is the same procedure. So we put a DM shape, then we measure with the waveform camera, then we do the crop, and then we have the data set. But we do also some data manipulation. So in the crop, we add some crop noise. So we add some X and Y misalignment in every sample that we take. So the neural network is more robust. So we don't need to have the same coordinates for every crop. We can do it like whenever we want. Then the parameters of the neural network that I train, it is the same as the shock Harman, but it changed the channel size because for the 3-sided pyramid is 3 and the 4-sided pyramid is 4. But all the other stuff is the same. So we put a shape onto the DM. Of course, with FAL, we get the phase cream. We decompose the phase cream into the 368 certainty. Then we put that onto the DM. Then we measure with the waveform camera, do the crop, and forward to the neural network, and we get the output certainty. So then we compare the output certainty with the input certainty and do the loss function, and then we do the backpropagation to the neural network. These are some results we have in our laboratory here. So we are closing the loop with weak turbulence. So you can see that we are closing the loop, and with strong turbulence also we are able to close the loop. And that's that's the thing I have for today.
Thank you, Rodrigo. Any questions?
What's the benefit of the function element in the shock Harman?
So is like too much cheaper than normal pirate. You're asking for the neural network?
You put a Chekhov number,
Yeah.
so the function you reflect it on top of that?
No. It is Shaq-Harman recorded onto the diffraction element. So we have an allographic recorded Shaq-Harman.
I see, I didn't know this. Okay.
Sorry. Khalid.
Can you comment a little bit on how you're producing and recording the programs? Like a general.
Well, general explaining, so we calculate some holographic computer-generated hologram, and then we put that onto an SLM, and then we do a 4F system to the photopolymer, and with some filtering we can record the computer-generated hologram onto the photopolymer. If you have any question with that, I can show you the bench where I record all this stuff. Feel free to ask me.
Any other questions? That's it.
So, replying to Mawa, she was saying that the Shaq-Harman, you can just use the traditional slope method or whatever for reconstruction, so
Yeah.
it's kind of linear. So, but maybe you should mention that how many modes you're extracting and maybe what
Yeah.
is the advantage of the
So we have this 4x4 Shaq-Harman. I think with the mobile repetition we only can get 12 modes. But with this method, with this neural network method, we can recover the whole 68 30 volts that the VM can represent. So it is a lot more than the normal classical reconstruction.
Other question? I have a question. Have you find some difference in using the Shaq-Harman holographic system on reality system, which you have like you are like using the same space for the diffraction holographic element, right? On the bench, right? So what are the difference between each one?
Well, the primary wave processor is a Fourier-based wave function, so you have to put it into the Fourier plane. And the Shaq-Harman is a Fourier plane wave function, so you have to put it into the Fourier plane. But in the propagation, I do some tricky things. So I have a tip and a tilt, so to get rid of the zero order. I can tell you in my setup there is more visual to see the.
Yeah, but which one is like easier to
Implement the primary.
What is more or less the efficiency of a diffractive system, because you have the different orders, so you maybe have to reject
We
part
are
of the light?
studying that for now. I don't know what is the diffraction efficiency of I just know the diffraction efficiency that the photopolymer prohibitor tells us. It says 93%.
Thank you. Let's thanks to Rodrigo again. So for now we have a coffee break. So let's be going outside right now. We have some information.
No, you can either stop here and we can go to the coffee break.
Yeah, the tree is right over.
Pero ahora puedes mostrarlo.
Yeah.
Y tú ¿qué quieres?
Oye, ¿intentaste grabar las pirámides con el dispositivo que hizo el chamaco?
Sí, lo intenté, pero estamos llegando al límite de resolución de los pero ya se me están haciendo distintas cosas para arreglarlo. Pero por ejemplo, grabé no el que tiene la pirámide, sino un difractivo
La cara de regazón.
No, eso también es muy complicado, pero grabé uno que conversió la red.
Es que te disminuye la resolución por culpa de que tiene que hacer geometría.
La cara del Nico no es difícil.
No, la cara del Nico
Es que es armónica.
¿No? Se lo tengo para allá.
Está lejos del límite.
¿Dónde está? Pero tengo cómo se ve, no cómo reconstruyo. Porque no
Oye, después venimos acá, ¿no?
Después empieza el taller.
Como que mira, dos pupilas para el lado.
Ya había entendido. Esa parte ya era ya, pero no sé si era si está vacío, podemos.
Visualmente con lo que yo veía era igual. Ponía el setting en de foco y hacía lo mismo. Como que estaba muy bacán. Y para ese difractivo el Nico lo entrenó con una matriz de 128% de que una base muy chica así. La weá cerraba en la
¿Cómo va a ser? Por ejemplo, ya, ok. Ahora lo que vamos a hacer es seguir con los códigos en Colab.
No, no vamos a tener los servidores de abajo del lado.
Ah, otro, ya, ok. O sea, ¿van a hacer demos acá o nos vamos a conectar nosotros a los servidores?
Hay que conectar sus servidores cada uno.
Ya. De todas formas,
¿Vaya a
van
enseñar?
Claro.
Sí, pero que mi computador tiene autolista, entonces mis dos computadores.
Ah, no puedes mostrarlo desde.
No, podemos montarlo desde el principio.
Aquí muy fuerte. Me dolió.
Lo malo es que no está entrenando en la red. No sé por qué no entrena.
¿Ahora?
Sí. Ahí está bajando, pero no sé.
Déjalo cortó el.
Ah,
is a slightly modified version, so if you download the tutorial 3 last day, you have to download the new one. Yeah, in the meantime, we try to solve this color palette problem. You guys could like arrange in groups. So I think with like 5 groups should be enough. So maybe 3 people or 4 per group, or I think so. So he's trying to change it to the colors because the contrast of this in the data is not really that good. There, perfect.
In this tutorial, we create a atmosphere based on PAO with Python. And he generate a random atmospheric base screen with a font karma algorithm, and create a dynamic and multi-layered atmosphere. Here is clone the GitHub with the function. We run and now here we it's loading. Here is the function we create a atmosphere here.
Yes, I think it's the HDMI is a bit unstable. So in the meantime, so as Benjamin says, this is basically we took some of the functions of OPAO and we re-implemented in PyTorch. And this allows to increase the amount of simulations we can perform. And we try to implement random phase generation using the Fourier method, but also we put the iterator to evolve the turbulence, and also we can stack an arbitrary amount of layers, considering the same parameters somehow considers, which is the diameter of the telescope, the R naught, the altitudes, and the outer and inner scales, and also the velocity and direction.
Okay. It's fine. We explain about Karman model and with a pre-parameter L0 and L0 do generate and visualize atmospheric phase wind and animate random, dynamic, and multi-layer atmosphere. And view certain basis on the pupil to project a phase on it and compare the true phase with certain reconstruction. We here is like the libraries what we were.
Here we have another cable. Hopefully this works. So this code is we are not going to go in too much detail about this particular code because we want to save a lot of time on working on the challenge. We are going to perform in the servers. So
right now is the code is running CPU. We change in runtime for you and change the runtime type and chose a GPU.
Yes, some of the people already use like all the GPU availability by Google, so some people have to stick with CPU at the time.
Yeah, Scuda is running and here is described what is the parameter for atmosphere with pre-parameter old scale and linear scale, and this function would create a random phase atmosphere and dynamic or infinite phase for atmosphere and multi-layer atmosphere. We set the number of pixels or grid size for the atmosphere or pupil. Here is the diameter for the telescope, and with this function we create a circle which simulate the pupil of telescope.
He's asking about what Google has at TPU. So there is this third device. Normally we use graphics cards, but then I don't remember the company who made it, but these are like tensor processing units that are more optimized to do tensor operations. So usually are a bit more efficient for training neuronal models. And then but I think they are more expensive to use in Google Class. But yeah, usually are more faster, but they are not like becoming popular. People still stick with GPUs, most of the servers.
And now we run.
Oh, I think you forgot to put the GitHub there.
Now it's working.
it's not working.
Well, it shows there.
Yeah. And here is create a telescope simulate preview with 128 pixel. And here I create one face screen with this parameter and to call the function with put the number of pixels. Sorry.
I got an error that doesn't remember which you use those.
Should change here. The device you can put in a string just CPU.
And here is define the number of pixels, the diameter of telescope, the parameter of outer scale and inner scale, the preview of the telescope, the device will run, and batch size. And here is a log we take the face we create and the plot, this face. And here create a face math random. We run anything and everything is random face.
So I think people familiar with OPAO can notice that it's really similar, the process. But I think the most interesting thing we implemented here is, can you go out a little bit when you call the function, Benjamin?
What?
Can you go up a little bit? So I think that the most important thing we implemented on this is the use of device. So then you can choose in what part of the computer you want to create a face, if you want to create it directly on GPU or create it on CPU. And we also implemented the batch size. If you remember for the machine learning tutorials, is that batch size is the amount of the size of this stack of the dataset. So also if you want a single face screen, you can just put one, but you can, to this function, you can request more than one. You can put 10 at the same time, and it's going to give it the face screen in the same tensor format. So this is going to already be prepared for training.
No.
So please, you can guys play around with this. Obviously, if you change the batch size, here we can only plot one. So if you want to plot, you can put a shape, like print the shape of the tensor, and you're going to see that it's going to be says 10 by 1 by, in this case, n by n. So as Benjamin put there in his slide, you can see. So this is, I think this is really useful. Oh, yes?
Can you just remind me, so when I look at the dimensions of the tensor, I do just the face size. I get 10, which is the batch size.
Yes.
And then I get 1, and then the dimension of my face.
Yes.
Can you remind me what is the second unit?
The one. Yeah, the one is reserved for channel, but I think in this context we don't use the channel too much, but for example, if you want to work with color, you should put the RGB in that.
Okay.
Or if you want to work with video, you can also put the frames in channel.
Okay. Thank you.
So if guys have any problems or questions on this part? Okay, so let's continue.
Here is I create a batch size with 10 samples with the same random phase atmosphere, and this function is down is create animation for this all batch size. You can run here and create animation with all batch size. It's changing.
So as you notice, this function is creating random initialization. So each time each item in the batch is going to be a completely random realization of that atmospheric parameters. Yes.
Hold on, sorry, I still have a problem on the previous slide. The previous slide, it is cannot initiate the queue down.
You can go to the last. As it comes up to that, so now they are displaying the 10 phases of the batch in an animation. Okay, that will look a bit more stable. No, no. If there is no questions, we can go to the other, the evolving turbulence.
Is this a standard library for the common phase clues?
As I told you, I just basically look inside the OPAO implementation and just start replacing NumPy calculations by dot calculations.
Yeah.
So it's mostly like a re-implementation. But then I have to do some tweaks to optimize, because I'm most interested in generating a lot of places quickly instead of to be like as physically as accurate.
And here in these cells, we are create a deep phase screen for the atmosphere. We set the same parameter and with that wind speed and wind direction and frame per second with the atmosphere is move.
So yes, I mean here is from the same function we downloaded. We are just changing the function, the object, and this object we can evolve the turbulence, and we added wind speed and wind direction, and also assuming some temporal correlation for the phase screens. But be aware that this particular part of the implementation is not completely following the OPAO method. I have to do a lot of tweaking to make it work on CUDA. So just be aware of that. It works really well, but it's not exactly the same as OPAO. So
here is this dot viewer is take 10 frames for this dynamic atmosphere and with plot. And here is the all 10 frames with smooth atmosphere.
So I think this is the important line, which called .evolve. So each time you call evolve, it's going to evolve the turbulence, and it's going to be stored again as a tensor for this implementation, I didn't finish to implement batch, so having like 10 evolving turbulence. So for this case, you have to only work with one turbulence for evolution. So yes, I mean, this is really preliminary work I'm doing here.
And you change this value and create 20 frames or the yes, with 100 here. Yes. Which is more phase is more different with frame because the frame per segundo is
Yeah, it's like assuming you are taking 10 frames per second with respect with the velocity of the wave. So it's the frequency sampling of the turbulence. So can you create like the animation as before? Or is this one?
This way is an animation.
Okay,
or
so
dynamic.
this is the same function, but now instead of putting in tiles, it's going to create the animation. So you can then check the. So this is a single layer. So then you can stack a lot of them of this and put it in different altitudes. But please feel free to play around with the R0 diameter of the telescope and see. And also, you can, if the guys that still have GPU can do like higher resolutions or more frames, and you can notice that the efficiency in the generation is really good. For example, Benjamin now is going to do 1,000 pixels per side. What happened? Yes, you are putting some in the plot. I think you are forcing some. Oh, yes. So you have to the function, you have to give it a pupil. So that's why we created the pupil in the first place. Then you can put your own customized pupil with spiders, obscuration, and it's going to work the same. So now the pupil is just like a tensor you send to the object, and then the turbulence is going to always have that pupil. So it's taking a while because the resolution is really high. So now it took like a couple of seconds. So and then you can see that the results are really good. So remind that this animation is adjusting the scale of the turbulence. That's why you can see some changes in intensity while the phase is evolving. But this is due to the nature of the plot itself, not the turbulence. So yes, that's why for when we do like high performance training, we can generate like millions of turbulence. And we needed to do it really fast. That's why we are trying to start changing towards CUDA computation for this. And I don't know if there is question with this part of the evolving turbulence. If not, I think we can continue. So
now I create a multi-layer atmosphere. During the code, we create the same parameters. Right now, the number of pixels, free parameter, and create the pupil. And here is declared the layers of the atmosphere with the same parameters. In here is the wind speed for changing for any layer, and wind direction same change for any layer, and CM port 2 we change for any layer, and rate the same.
So for this, we take the approach, probably it's not the most efficient one, but I don't remember how OPAO does multi-layer. I remember that OMAO, you only have to put like an array if you want layers of R nodes or wind speeds. Instead, we choose to do a dictionary, because then this dictionary you can store it as a JSON file, and if we want to test the same turbulent conditions across different students or different experiments, we can have like a more consistent way of sharing that properties, and for reproducing results is also easy. If you have like a experiment you performed like a year ago, you just look the file and you quite exactly know what turbulent conditions we try to replicate and replicate. So this also comes with a seed that you can set it up. It's not here, but you can also put a seed, so if you want exactly the same realization of the evolving turbulence, you can also replicate that by putting a specific seed.
Here is the same flow. Same results with the seed. And here is create the same animation for the multi-layer, the atmosphere.
So this is the stacked 3 layers. And of course in the dictionary, if you want to have more layers, it's just to put in the dictionary how many layers you want with what properties. So I think for readability it's really easy. Probably it's not efficient in the code itself, but for the human creating the profiles, I think it's really intuitive. Yes?
Maybe I missed it, but when you talk about multi-layer, are you considering somewhere the field of view?
No, I didn't consider field of view because as I mentioned, this is extremely preliminary, and we are just focusing on generating a data set. So, and when we train, we did not consider like different field of views.
Yeah.
But yeah, I mean that is should be like an interesting step to go through. Start adding more and more physical parameters to hopefully be closer more to OMAO compared with OPAO. But yeah, I mean, I think I'm extremely focusing on the efficiency. That's why I make a lot of sacrifice on the way. So yes, I know if there is another question. I mean, I try to make it as simple as possible, this part. You can go and inspect how we create the classes, the functions, and see for yourself how was exactly implemented. But for the purpose of this tutorial, we just go where you have to trust me that the implementation is good. And
So what you do now is you stack these 3 layers, or one on top of each other?
yes. So the animation is the contribution of the 3 layers.
Now I decompose this phase screen or random phase screen random fit with Cernic. Why Cernic is we want to compare 2D free mass into a compact vector for learning, and Cernic and stand in optics or AO, and allow recognition and visualization. The pipeline is built basis of the Cernic, project this basic interface, and reconstruction this phase with the Cernic coefficient, and compare. Here is the code for the pyramid wind processor. Is the phase.
This is the same code we already shared. So
and here creates the face. So the brainwave sensor in the blood, and this is the important part of this code. We create a magic interaction.
So yes, this class is the purpose of this is more to do linear reconstructor, but inside of this class there is a function that creates Cerny modes, and then you can convert face to a Cerny mode decomposition or backwards. So Cerny modes values you can get like a compiled face, like constructed face.
And here is
So this
the
is
number of the Cernyx with discomposed. The
Yeah.
the 200 modes.
So we use the Omao style of creating this Cernic index as a vector of what Cernic modes you want. But remember that with the difference with MATLAB is the index starts from 1. So here piston is the zero mode. Tilt is going to be 1 into.
Face over here. And here is create a random phase screen of the atmosphere. In this function, we take this Cernic mode for atmosphere, and the other function is recreate the phase with Cernic. We take the atmosphere, and we plot. We take a phase random atmosphere with a representation with Cernic mode.
So yeah, I think this is pretty straightforward, but I don't know if you guys have some questions. You can play around, you can choose, you can try different Cernicit. It's not necessarily that so that you put the start and the end, but in the variable, can you go up? In the variable G modes, you can create your custom vector. For example, if you want to use like the center of the pyramid of the Cernic mode, then you can put it there, or just the higher modes, or just each two modes. So this set G is just to generate the vector, but you can put your own vector here in the G modes parameter. And of course, we also we implemented if you want to create it in GPU or CPU. And also put your own custom pupil if you have log obscuration, yes?
Maybe if you get it, why is the maximum 400?
Oh no, I mean that comment was there probably you can put any Cernic modes you want. But you have to be aware of the VRAM, so especially if you want to create it like inside. So
It's great. 10 Cernic mode phase.
oh sorry, can you go up? So and the no a little bit more. And if you notice, we also put in the pyramid. The reason of this is we create this function more to do the linear reconstructor with the pyramid. So that's why. But inside of this function, there is the other class that is just generating the Cernic modes. So this is not so generalized as we should do. Like, for example, probably this is not going to work if you put like a Shack-Harman here. So also please be aware that this is also really preliminary and most focused in our works.
And here is this cell. We create a dynamic atmosphere. We take the Cernic mode for everything frame the atmosphere, and reconstruct this phase with Cernic, and we rest the reconstruction with the phase original, and we have a residual with animation here.
This animation just showing the Fourier phase, the Czernicki modes, the composition and the high frequency of the residuals.
Right now, it's the Cernic mode is 10 only clear mode because more. Right now, is the Cernic phase is 200 mode and little bit more better with the residual.
So, as you see, this is still pretty straightforward. I think this part of the tutorial makes you feel like closer to home. And I don't know if you have specific questions. Or also any feedback that you say, no, your simulation has bad physics in it. Also is highly welcome because we want to improve it. So
Not so much a comment on the physics or anything like that, but can we add like a color bar like mapping? Because they all go from 0 to like. I assume the dynamic range on the first graph is a lot wider than on the residuals.
probably
Right
yes.
now it's not possible to tell.
I'm not familiar with this kind of notebook implementation of the animations, but I think you can put a color bar there. I think individually are having each one of them has its own dynamic range on the display, so that's why you say it really bright. Maybe this will work.
I don't know.
Okay, we will try to put the color bar.
Try putting in the iron kill as a label.
Yeah.
As a label.
But you need to locate that.
Benjamin, you put PLT dot color bar.
And then,
You
just
have
like inside that parentheses, as long as you put which specific IM you want to into or something, that should be fine.
you should put in 3 times, like in two, in one.
That won't work.
I mean,
Here, you only get it at the end.
oh, no, I
Oh,
was just trying to.
no, but you have to put it after
No, I
to
was just trying to
create
put it
in
last one.
1 and 2 and 3, like at the end, like here.
The problem is
Color bar,
because
color
of the
bar,
left
color
one,
bar.
I
PLT.
thought I wanted to see how much RMS you see on the first one versus the one.
And inside the brackets, inside the parentheses of color bar,
This is the residual, so
Put
I
in
don't
one.
actually see the residual, not like the full phase itself.
But the residuals are
and
only
repeat the same for the others. Oh, so we with that change Benjamin is doing, thanks a lot for figuring out. You can see each individual color bar and get a glance of the scales. All has a fixed color bar. Thanks. So I don't know if there is more questions or some comments.
Maybe one question, like, of course you have a model by which you can generate these face screens, and you take some free parameter, and based on that you generate the face screens. So the face information that you see, is that compatible to what you really see depending on I don't know, a certain location in the free parameter?
That is a good question, and we still have a lot of debates in the laboratory about that, because we try to replicate like some phase distributions across data sets for different toolbox and differ a little bit. So for example, OMAO tends to be the deviation of the phases tend to be much higher compared with OPAO, and this one is kind of in the middle. So I'm not a physicist, so I don't have like a strong opinion on which more is more realistic. But I mean, if we are open to hear feedback of if this is a good enough representation of what the turbulent conditions we see in real life. But we used to trust a lot in OMAO, and we changed to OPAO because a lot of the devices we have in the lab work in Python, and we try to do more straightforward implementations. And then we start developing this one because we want to do it faster. So, but yeah, I mean, in the physics side of things, we are not still sure which of the three we should trust more.
The finish is create a data set on data loader with this face screen with save the face and the variable x and the y. The variable x is a certain coefficient. And here please create call the function, and here it create the class of the data set which create. We take a random here. We take a random small field and take to certain coefficient. And the same function of the pyramid.
So this basically is the same concept we explained on how to create your own data sets managers. We only thing we are changing here is that instead now of calculating random stuff inside, we use our own built-in function to generate faces and using that one as a face generator.
And the print is the byte size, the channels, and the number of pixels of the face map. And is the y variable is the certain coefficient, the last one.
So here I think you can notice something is that we are going to train image to vector. You can put directly the 197 here instead of 1. That works, but for we try to make things like sure that we want to avoid like crosstalks between channels and vectors. That's why we always keep the 1. It's just a safety measure when you are building your own custom models. We try to keep the same notation just to avoid like For example, if Benjamin implemented a model and use another notation, then the model is going to give errors on by testing. So we try to make all people in the lab make sure we use the same notation. It's just for that.
On the last cell, we print the base with certain coefficients in the plot, and here we can change the data, the batch of the data. We take the first data, and the last one is all random phase and with certain mode.
Yes, and now the contest we have preparing to do is basically the same as before, but instead of just estimating tilt, we're going to try to estimate like 10 30 nodes with the pyramid. So it's kind of like the same you already do, but now a little bit harder. So, but the idea is going to be the same, just try to get the best, the lowest residual as possible. But this, well, for this you are going to have more time. We are going to help the groups individually. So we want to make this as fair as possible.
Here's the reconstruction of the base with this learning mode.
So yeah, I mean that is the end of this tutorial. For the code for the contest, we have to do it in VS Code because it's the most straightforward to connect to the servers and manage the GPU there. So you are going to see that the code is going to be a little bit more confusing, but we are going to be with you guys guiding it and helping to build your own training or your own data sets or your own models. So please be assured we're going here out to help you guys. So I don't know if there is questions. I see some nervous faces. But I mean, at the end of the day, it's just have fun, try to make it work. Probably nobody makes it, probably everybody makes a really good result. Most of the time when we try neural nets, we have to try like 10 times before it starts working. So don't be too worried about it.
Is it just completely trial and error, or do you have like ideas of?
It's kind of both. Like at the start, it's just trial and error, see what fits. But then when you do it too many times, you are developing some like experience on. Okay, maybe I should start with this. But yeah, at the end of the day, if someone says that they have an empirical way of saying what is the best approach, it's lying.
Do you use machine learning to make the best machine learning?
Oh, that is interesting question. So there are some models that optimize the best, like for example hyperparameters. They call it like meta learning, but they are extremely computationally expensive because they have to train a single iteration is a model that has to be trained and measure the performance, and then back propagate to extract a variation of the model, train again, and so on. So it's a power of 2 scaling the computational expense. So I don't know if there is another questions, some concerns.
I do have one more question. So you mentioned about certain models, right? I think it was 5-6 years ago I used this object-oriented adaptive optics model, which also is in method.
Yeah,
I think it was
OMAO.
made by BMT
Yes.
people. So like you mentioned about different models. So I'm wondering, like, if you create the same parameters, you use the kilometer, like how far above from the surface the layer is, choose the right parameters. Do these models give different data information? I mean, it's more towards physics and sense.
Yes.
Because at the end, I would like to, you want to create a model which is representative of the real situation or close to it?
Yes, I mean that is a really good question, and in our experience, we dealt with that problem a lot. So, for example, Camilo, that's recently showing his results on the transformer,
Yeah.
he used OMAO for training,
Yeah.
and it give really good results. But then we use our own custom for the diffractive optics because I need the generator to be differentiable,
Yeah.
and I cannot use OMAO for that. And we took a lot, but I tell you, a lot of time to trying to match the results that got Camilo in with the other simulators. Or, but I cannot tell you, in my experience, which of the two are more robust to real life conditions. But I think we have, with as Professor Esteva mentioned, that we have a huge precedent that Benjamin was able to close the loop on the sky with a neuronal net that was trained in OMAP. So I think with that antecedent, we can start having something to say about which models can be better for training models. So, but we also now we want to also try a model we train with OPAO on the sky and also with this on the skies, and then after that I can tell you, okay, this one give you our best.
But behind this model, can you see what analytical equations are there? Because at the back end of OMAO, you can really see.
Yes. Here you can see it too.
Okay.
It's the same as the OPAO. Use the same equations of the von Karman stuff.
Okay.
So I try to do it from OMAO, but OMAO has a lot of equations that I don't understand it. I have some weird value that I'm not confident in changing. And I saw OPAO, I saw it like it was most straightforward and simple, and I just started. But I don't know if, okay, yes?
So, from my knowledge, and someone that knows it better can correct me, but both OMAO and OPAO are just doing an implementation of Asemat's algorithm for the propagation of a phase screen. And from my test, I generated a bunch of phase screens, applied the structure function, the theoretical one, over the average structure function for many screens, and they both converge just fine.
Oh, okay, I mean that's
Within like a percentage point after like 30 seconds of data.
that's good to know.
You shouldn't be overly worrying about like, am I getting 7%? Unless you really need really precise screens with like 10 to the minus 5 precision, I don't think you should be overly worried about the fidelity of the screen. At least from my experiment.
That's really good to know. I mean, I don't know if someone can share also his experience, because you guys have more experience with turbulence simulators, where I'm just the computer guy that programs stuff.
David, in theory you could train using white noise, and the thing is that the model will learn. You don't need the exact same statistics, as long as you're like you have a wide variety of something. It can learn. Anyway. Well, training on white noise is really difficult to do, but that means that basically you're not really constrained to have the exact same statistics and exact same shape and everything, because it's a stochastic model.
Okay. So yes. So basically we want to make sure that, because we strongly rely on doing this kind of simulation to experimental instead of getting experimental data to train. And up to this point, we are really having really good results. So, but if we want to convince some physicists that our results are good, I mean, that is the part where we start to struggle or start to be worried about. But yeah, I mean, that is a good feedback too, because we want to be sure that what we are doing is right, makes sense. can you, Benjamin, show the code? So we have some laptops with VS Code installed, so but I'm not sure how many we have. If some guys have already VS Code installed, we can guide you to the process of connecting to the servers. Okay, so Benjamin is now going to connect to the server, and he also have prepared the serial, the IP address. So
I six group, six Fairfield, one choose one.
yes, we have two main servers called McCartney and Lennon. So and each of them has eight GPU cards. So we have plenty of GPU power for all groups. And you can choose any of that IP IDs. I think for the people that are going to install VS Code, you just download it from the official page, and I think we have to download the SSH remote server. It's an add-on you can download inside the application itself. We can guide you once it's finished. If everybody got a picture of this, then Benjamin can show you how the code is, and we can try to explain it a little bit.
Too fast.
Too fast. Go back to the. Okay, so now we can go on to the code. So if someone has already installed VS Code but doesn't have the add-on needed, you just go to that icon with and add SSH. Is the first one, right? Remote SSH.
This one is here.
Oh yeah, it was backwards. Okay. We are not IT guys either.
The user is go up to
So this icon on the bottom should appear like two.
buy your
is the
pizza that I got for
competition.
free.
Yes.
In the system.
Okay, fine. Just stop. Poi este.
Remote SSH
Now we are you ready with the right the button? Go and search the IP.
SSH. User. Add IP.
This 46 or 45 is all servers, is two servers. No, Jose?
do you want to join?
You guys remember that you have to choose one because if you change the code, you are going to change the code of the other group. So can you? Put the so raise your hand. Who is go? What group is going to connect to the first one? Okay, so this one is taken. So the next one.
Second row. Second row.
Can we pay attention?
Okay. Third. Third.
Which one? The third?
The 246 third is which one? The one.
Okay. Who else want to enter the challenge?
We have a group here.
Okay, 245. Two.
Workshop too.
And the last one? Who wants to try? Okay, the last one.
Workshop, 1, 2, 3, 5. No, the group workshop, the name is the user. What group? Yeah. The IP. It's I don't know.
Okay, so
I only have one meeting.
No, la dejaron yes, we have the codes of the GitHub, so now you can push on there. So first we want to connect to the terminal. So Benjamin, can you show the terminal? On what they should expect to see in the VS Code? A cualquiera. Sí, no la vamos a hacer. So you should see, if you open a terminal, you should see this one. If you are in McCartney or Lennon, and the user. So if you saw the user, we provide you with the McCartney or Lennon, you are already connected, and we are ready to get the codes from the GitHub. Well, you are connected to our Wi-Fi of the lab right now.
The app can go up to, say, 2 meters.
No, anyone? It's not connected yet.
Hey, did you get an answer from Ezra?
You guys connected? Anoche comí, pero
They got 3 days.
Right now I have
Except all the cookies, take all my data, yes. That's the fastest way.
Vamos a hacer lo mismo. Vamos a
if you guys write LS, command LS, now you are going to see a folder. Perfect. You are already connected, right? If you click LS, you should already go to the folder. You can enter there and you can find it. So if you guys write LS here, you can see the folder, so you can open with PS Code. Machine learning. But you can open it like file open.
This is already like a
Yes. So open folder. And machine learning. The password. Trust. You trust me?
I trusted.
Now you can see the form.
For me, the response rate of Andre is scary. It's super fast. It's scary. Why? I'll tell you why.
So you are ready? Oh no, it's already closed. So we can answer. So everyone got inside the tutorial 4 notebook inside. Okay, what can You're able to open the... Okay, cool. How much quality? Beta.
It's all related. I'm saying
If they ask you where to run the code, you just put base. And by Python environment, Python, it says Python environment, right? That is like
No, but
I'm just trying to repeat, just play button. What happens then?
this one?
Yes, it's selected, sir. On medium base. Okay. 113.9.
Come on.
I don't have Mac.
Then you effectively like a remote desktop, right?
yes.
No, it's a remote desktop on their server, right? You actually
I'm on their server.
I just made Python.
Yeah, but you can set that up.
Oh, those are,
Yeah, on Mac.
I don't have it. I don't have a set machine, then you don't have to install it in advance. But anyway.
It's all different.
but it doesn't show it there, though.
Yeah.
Drop down section.
Press it fine. And then you have magic in this one. Then why is it you trust to you use the Mac is nice control. Which one?
Oh, you can. Because I feel like because you don't
Right now you have the Python today.
because you don't use a platform like
What step we did? I think we find what are the first step we did?
I show it to you like that as well.
Yeah,
IT
Explorer.
department says you computer will
then
install.
open window. I don't buy it. That's why.
No, no, this is TNO.
Oh no, I'll let you do it. It does that.
My problem is if you want to do something with white bars on a machine, don't do this. Just buy a machine and register an IT network. Because you have when I was doing some background. No tablet, no trust. Just buy a laptop. And ask for it when they come to Explorer and they have the tutorial.
That's fine, but
For me, the reason was training. That's why I bought the.
Yeah.
Yeah.
let purpose to be.
It's so it is founder everything else is already for real.
So we use the lunchtime for that. Then on the way back, I mean, hopefully we get something else.
I don't know that it's relationship with this
I don't have a copy. You're coming out of the blue for me. I'll send it to
This one? It's not a project yet. It's a discussion that we're having with Cody.
See, I think it's running with an Instagram.
No, not yet.
Yo creo que allá igual. Porque yo
You guys,
I think we passed the bottle from lunch with already big coat because I think all take longer than
Close to play our foot lane. Zayla?
What's it like?
File heights foot lane. File heights music.
funciona.
¿Sí, Nelson puede correr? Sí, le pueden hacer de
Responsibility, yes. Then when you ask somebody else.
No, si eso no tiene nada que ver. Siempre que estemos con varios tienen ese problema. Me parece que el 10 con el I think the problem is that it's like running because this has to be about the kernel. For some reason the VS Code cannot find the Python kernel on your computer. So we can borrow you a laptop. I think it's faster. I gotta go. I will do later because we have to go to so where? I have a meeting. I have to go. But then eso es lo que vamos a hacer. You can repeat. Pero sí, Benja, ya está listo aquí. Ahora no, sí, pero como la había visto, after before lunch, we should explain the code and okay. Perhaps something to think about like
Bueno, hay que salir a 15 minutos salimos de acá. 15 minutos.
Me quedan 5 minutos para...
We open folder?
Muy poco. You are guys are one of after lunch we start training in groups and
Entra una imagen y te hace. Eso lo queríamos hacer, porque te hace como los símbolos y después pasa a
Okay, cool. So basically, Benjamin is going to finish the help and is going to explain the code. And then after lunch, we will all training and tweaking. And then we're ready. When you are ready, you give your network to
y después todas esas imágenes van a obtener de alguna forma información útil. Y todas esas imágenes se combinan en la segunda parte de la
part of the challenge. What you want to do.
64 imágenes y cada una se una compañía
No?
y esta segunda
Guys, Benjamin now is going to explain the code to be prepared, and after lunch we are going to tweak. The groups are going to tweak the model to train it, and then we are going to test it on whip or stage. So
Here is the number of the GPU was used in the server, and here is many examples with great data. It's more faster. It's the progression of pyramid make a circular people, and here create again create a people the pyramid base and the preparation and resize and crop the preparation for the same number of pixels of the people. And here is preparation with phase atmosphere. We take the phase preparation with the pyramid and keep the tubes and reshape and crop and resize the tubes. Little function for add noise and normalization. We run, take this image for the pyramid waveform sensor with add noise and normalization with zeta score. And here the same function is loaded again. This function is for create a basic or certain mode and build setting. And here is create the class of the dataset for phase and certain coefficient for the training. and here we generate the pyramid version sensor, and here calculates the sending mode in this function. And we create a little tiny net, the same of the tip tilt, the yesterday.
If you would like to use sound, you said you create learning emotes, you mean like you create learning emotes on the propagated phase, right?
Yeah.
Yes, so you're basically preparing the data set from
Phase.
the face reading.
Intensity phase, but in the my propagation with the training, we take the propagation and keep the people, the pyramids people.
So, but you're feeding the learning emotes before the front wavefront passes to the pyramid.
Yeah, before.
Yeah.
We take it the phase.
The composition of the face.
Yeah.
Without any forward. So this is just preparing like the data set, like the real values and the input data to start the training.
Here we create the same net for tip tilt yesterday. The same, right?
This is the network you're going to put work on how to improve this. And remember, this is going to be trained on the experimental, so you also have to figure it out the noise, maybe add more noise, less noise.
Okay, so to validate and understand the change, so you first fed all the learning about certain number of modes to the input wavefront, and once the wavefront propagates to the pyramid sensor, you will estimate them somehow.
Yes, the goal is
then you will match.
yes, the goal is from the pyramid images, estimate the Cernic mode. And by that, we create a data set of known Cernic modes, given pyramid estimates.
He create the validation and training function.
So you remember for yesterday, this is the same, right?
The same.
The loader, input-output data, forward, loss, and backward. No, sorry, this is validation. This is backward. So the same 3 steps. There is nothing different.
And here is a parameters of the training with the number of the modes, the coefficient scale, the pixel size, the pupil, the batch for the training of validation, the epochs, and the learning rate.
You can take these parameters. You have to make a lot around the case. So maybe more batch size is going to be more effective, less resolution, and of course the learning. We discussed a lot of the learning rate, how it's important to fix some value but then try other ones. So that is also the part you have to put a lot of work.
And he creates the training dataset and validation with 4000 data and 800.
For consistency, guys, all groups should keep like the same amount of data set because of course if someone put like 1 million data set, probably is going to win no matter what. So try to keep it this consistent across all system. Yeah, God no.
And here create the training data loader and the model with put on device, and we call the optimization Adam and the loss function. And here is create a loop for training and validation and the keyword of the training.
So this is the training loop. So this is the part you are actually training the model. On the bottom part. Oh, then here in the bottom part of your interface, you can see the memory consumption. So of course, you can see like oh, I put, if you put like a large batch size, you're going to see that the GPU consumption is going to increase. You also can take a look at that.
Are you predicting scales here, or is this without it?
No, it's 10 something more.
But,
10 or more.
but it includes so this is still included on the problem. So you cannot cheat by removing tilt.
Felipe, the number of modes can be modified?
The number of modes. What's the DM number of modes?
68.
So 68 is the maximum, but of course we want to make it this a little bit easier because then we have to train like one day. So we just keep it like 20 maximum. And of course this is the same print, and you can go in checking how is your training going with the validation and the RMS error. And you can notice that the example itself got a really good result, so you have a good start. But remember, in order this to work on the bench, you have to add a bit more noise. And that one is going to be a little bit harder to fit, so that is part of the challenge. So that's all the code. So if you have questions, or we can discuss it in lunch.
What is the noise parameter?
Where, Benjamin, where is the noise parameter you can change?
This is function for noise?
But you are using the default, right?
Yeah.
So here, if you change this part of the function, you are changing the conditions of noise. You can activate or deactivate using photon noise, and you can, this is read up, right?
Yeah.
So you can tweak these parameters to be avoid noisy conditions or noisiness conditions. If you put 0, you're going to win in simulation, but in experimental, yes, this is going to be tested on the bench.
Can you call the add noise different?
Oh, okay.
Like right as well, like training.
Oh, okay. Okay, so sorry, this line, when you put that noise here in the training loop, but this says show predictions.
This is only for the visualization?
Yes, but looking if
Okay.
in training there is no noise?
No.
Okay. So just modify the default values of the function. Okay guys, I think that's all. If there is no more questions.
We can change the noise distribution.
Oh, that.
We can change the noise distribution because it's Poisson.
So by default you are adding both Poisson and Gaussian. Yes, so we are considered both readout noise from the detector and photon noise from the. So I think it's convenient to keep both.
Okay, guys, now that you are almost there, like experts, so we shall move for lunch time. So we will resume whatever we are doing, but we will do it in the lab. So we should take whatever you have, we'll leave it in the lab in the meanwhile, and we will keep working there because we will closer to pulpos. Pulpos like people to be around, so it feels more comfortable and we treat you better. So So yeah, please take all your belongings. We'll stock them in the lab. We meet and we go for lunch.
So it's like
Try to emulate like real conditions.
Up to the pixels go down.
What do we need?
We need to take everything.
we need to take everything.
Yeah, leave it in the lab.
So, yes. So, if I don't go to the second lab, can I just come back and pick up, or it will be closed after the lunch? Me too. I have belongings in this and this.
But you are going to go back to the lab after lunch with us.
Yeah, I'll go back to the lab, pick up the belongings, and go for my lab.
But after we go, or you have to look early.
I have to early, something to after that.
Probably, I was asked if someone is going to stay in the lab. Because everyone in us is not like.
Then everyone is, I mean, if everyone after lunch will get then I can access my stuff. So if you go down to the lab, then